Okay, so we're going to talk about training tests, training error and test error, and the big difference between these, just for illustration purposes. So we're going to do it using this simple toy data set, which is, well, it's not a toy data set, it's a real data set, but we'll see that there's a couple of flaws in using this data set eventually. But the data sets, each row corresponds to a different country, and then each column corresponds to a different indicator. So for example, air pollution, assault rate, the employment rate, homicide rate, and so on. And then the response variable that we're going to use in this problem is life satisfaction, and then we're going to regress it onto all of the other variables, including GDP per capita. So this is just an illustration of how we could use, for example, GDP per capita to predict life satisfaction. And then, so this is just processing the data a little bit, turning it into a Y and an X array here. Okay, so I'm just going to define, I'm going to wrap the linear regression fit and then the predict methods into these defs. This is just because I want to use, I want to make very clear that there's a separate fit method, a separate predict method here, and then I can modify these later on down the line. So yeah, so let's skip that. Okay, so we'll return to that example in a little bit, but first let's talk a little bit about risk and empirical risk and these concepts in machine learning. So if we're given a loss for our set of parameters and for a given observation x and y, then we can think of the risk as just the expected loss for that given parameter, right? So if I were to propose, for example, a set of beta coefficients for my linear model, and if my loss was square error loss, then my risk would just be the expectation of the squared error for that given predictor. Right? That's my risk, or sometimes it's called the true risk of that given that set of parameters. So if I'm given training data, which is just my xi, yi from I going from 0 to n naught, for example. And if these are drawn independent and identically distributed from some joint distribution between x and y, then the empirical risk, so that's an assumption that we're commonly going to make, is this IID assumption. Then the empirical risk, we define it to be this R sub n, which is just an estimate of the true risk using the training data. So if I have some fixed parameter theta, then I can average my losses over the training data, or over my data n in general, and I can compute this thing which we call the empirical risk. And of course, by linearity of expectations, if I take the expectation of Rn, that'll give me R sub theta because it's the average of the expectations of the losses, but because they are IID, they're all the same expected losses, right? Which is the risk itself. So this is why we like to, for example, minimize this empirical risk, the average of the losses over the training data. We like to minimize it because it's a reasonable surrogate for the true risk. And the true risk is sort of what we want to overall be minimizing, right? Of course, we don't have access to this true risk, and so we have to estimate it, and so we do it with this empirical risk. So any estimator that is a minimizer over some class of this empirical risk, we call that an empirical risk minimizer, or ERM. And the Rn empirical risk is sometimes called the training error. So ordinary least squares is an empirical risk minimizer. but there are two things that we have to specify. First, we have to specify exactly what the prediction function is. So these are linear functions. So that's one constraint, is that we're predicting using linear functions in linear regression. The second constraint, the second thing that we're going to specifically do, is use the square error loss. So for linear functions and square error loss, ordinary least squares minimizes this average square error loss for the linear function with respect to the beta vector. So ordinary least squares fits within this empirical risk minimization framework. It's empirical risk minimization for square error loss and linear predictor. Okay. So why is empirical risk minimization a good idea? So like we said before, Rn is the expectation of Rn, if we were to fix theta, is equal to the risk. And also, if we fix theta, we know by the law of large numbers that Rn actually converges to R theta because it's an average of identically distributed variables, these losses, which have expectation Rn. So that's what we know from the law of large numbers. So that's why empirical risk minimization seems like a good idea to begin with. So let's go through some examples of empirical risk minimization. For binary classification, an example is we are a mortgage insurance company and we pay, we're an insurer, and we pay the mortgage company if the insurer defaults on the loan. So a person takes out a mortgage insurance on one of their loans, and then we have to pay the mortgage company if they default. Right? We have to determine how much we want to charge based on our prediction of whether they will default or not. So it's very important for mortgage companies or for insurers to predict whether they default or not. So for example, if an actuary says that people that are young are irresponsible, and then people who are young are irresponsible and they're more likely to default, then really this person is giving me a prediction function, right? So what implicitly they're saying is that if we define X to be the age of a person in years and YI to be if they default, then they're predicting that they're predicting a 1 for default if the age is less than some theta equals 30, right? And now we could define a loss to be, for example, the 0-1 loss, whether they were correct or not. So this person, this actuary, is predicting default. Just to recap here, is predicting that this person defaults if the person is their age is less than 30 or not. Now we get to see whether they actually did default or not. And if they're wrong, then we give them a loss of 1. If they're not wrong, then we give them a loss of 0. And that's what this indicator says, is that this evaluates to 1 if their prediction matches the actual response. So now the risk is this expectation of this indicator, but we know expectations of indicators are just the probabilities. So the probability of the prediction being wrong or not is the true risk. Right? So now we can ask, how well did this person do? And we can evaluate, for example, this over some data set, right? The empirical risk over some data set. And now another example, that was binary classification. Another example is unsupervised learning, right? So typically we are thinking of losses in the supervised learning context, but it also holds for unsupervised learning. So we want to summarize, compress, or learn a distribution of X. That's the basic idea behind, that's what unsupervised learning is. Clustering is an example of this, where we just assign each datum to a cluster, right? So for each data point, we say they belong to either cluster 1, 2, or 3. That would be clustering into 3 clusters. Right. So for empirical risk minimization to work here, we have to have some notion of loss. So now the basic idea is that each datum we are going to assign to a cluster, and then this cluster has a cluster center, right? So we're just going to say that cluster 1 is associated with the, for example, average of the datums within the vectors within that cluster, right? So if we think of all our parameters as the cluster assignment, which is just a mapping from 1 to n to 1 to c, so if we think of it as the parameters as the assignment and these centers, then we can associate a loss. So for each data point, we can say how close is the data point to its cluster center, and we can square that distance, for example. And so that's our loss here. And since we have a loss, we can average this over a data set, and we can call this our empirical risk, for example.